Petri nets in engineering. The usability of the Petri nets in engineering applications is as well widely accepted. The stages of the design, the implementation, and the validation of systems are suitable addressed with Petri net models. The covered applications include communication protocols, distributed systems, distributed database, concurrent and parallel programming and systems, industrial control systems, multi-core processor platforms, data flow computer systems design, workflows and process-driven systems, fault-tolerant systems, and to mention a few. Properties practical interests such as fairness in the execution of tasks, deadlock avoidance, state reachability, process interlocking, among others, are possible to be analyzed within the Petri net framework. For example, illustrates a very simple and conceptual communication protocol. The communication act is analyzed from the sending process point of view. A sender process sends a message by the output buffer and blocks its activity while waiting for an acknowledgement by the input buffer. A receiver process is blocked while waiting for an input message. Once a message has arrived, the receiving process reads the message and sends an acknowledgement by the input buffer. After the communication act has finished, the process restarts its logic to be ready for the next communication. This model could be extended to include faulty communication channels, which may lose the messages, acknowledge expiration periods, or other characteristics of practical interest. The analysis and design of communications protocols has been widely addressed with the use of Petri net models. A Petri net representing a communication protocol. Process 1 sends a message by the output buffer and waits for an acknowledgement by the input buffer. Process 2 reads the message from the output buffer and sends an acknowledgement by the input buffer. After the communication protocol is completed, both processes restart their logics to get ready for the next communication act. There are some extensions to the Petri nets to handle specific aspects of different engineering problems. Some of the extensions add structure and information to the tokens, transitions, and places of a net. These extensions allow the construction of models that are quite compact compared to the models obtained with a traditional approach. These models are called Colored Petri Net, CPN. As an illustration, depicts a CPN for a task scheduling problem. The structure of the net represents the different stages of the working processes in a distributed multitasking environment. The left-hand side of the net structure represents the stages that the processes perform to acquire a job. The right-hand side represents the stages that the working processes perform to release the resources and update the state of the overall scheduling problem. The simulation of the model depicted in the figure allows to study the performance of different scheduling policies over different workload conditions. For example, it is possible to approximate the optimal number of process required by the scheduling problem for a fixed number of tasks. Even more, it is possible to study an optimum rate in the increment of the working processes given a rate in the increment of the tasks over a discrete interval of times. A colored Petri net model of a task scheduling problem. The structure of the net represents the different stages of the processes in a multitasking environment. The working processes compete among them to acquire the jobs that need to be executed. Each token is a composite unit that carries the information about the state of the working process. The simulation of this model allows us to study the performance of different scheduling policies. Recently, with the increase of the cloud computing and the massive data content in the social networks, the machine learning techniques and the methods related to the data analytics are essential tools in the study and investigation of the big data. There are several proposals to allow the Petri net models learn some kind of fuzzy reasoning and decision making. Similar approaches as that of the supervised and unsupervised learning have been addressed. Shows a Petri net representing a workflow pattern for a customer reclaim system. The customer may initiate a request at any time. Two activities are launched in parallel once a request is in the system. First, a ticket check process is executed. Second, an examination of the request is performed. At this point, based on the machine learning, data analytics and/or statistical learning mechanisms, guards for the transitions B and C are constructed. The guards allow deciding when it is more convenient to execute an in-deep examination process or a casual examination process. On the one hand, it saves time by executing a casual examination when the guard determines that it is more likely that the characteristics of the request are that of a genuine customer request. On the other hand, It saves money by executing a thoroughly examination process when the guard determines that the current request is more likely to be a fraudulent request. A Petri net model for a workflow pattern of a customer request. The customer may initiate a new request at any time. Two activities are launched in parallel for every request. One activity is to check the ticket. The other is to examine the request. At this point, a decision is made about how deep to examine the request. At this point, a guard based on the machine learning and data analytics is constructed for the transitions B and C. A decision process then comes, where either a compensation payment, a request rejection, or a request reinitiating may apply. Other important area of the engineering where the Petri nets have been successfully used is in the automatic code generation. The exponential growth of the cloud computing and proliferation of solutions based on the Internet of Things have made the design of the system software supporting them become more challenging. The set of requirements that this type of systems must address includes the sensing of signals in soft and hard real-time and the traditional support for media reach services. This mixture of requirements turns the design of a correct and efficient system of this type a whole challenge. Approaches based on model-based design promise useful solutions for these challenges. The complex behavior and set of conditions that this class of software must address can be well represented with Petri net patterns. Synchronization mechanisms, message passing, rise conditions, critical sections, parallel and concurrent process, task activation conditions, and user interactions, to mention a few, could be easily represented with intuitive Petri net blocks. Then, a simulation process may allow the study of the performance of the solution and the adjustment of parameters for a fine-tuning process. Represents a Petri net model for three parallel processes. The transition T1 launches the execution of the processes in parallel. Each process runs freely until they end its activities. In this design, the transition T5 synchronizes the end of the processes. That is, if one process ends its activities, then it must wait the others to end. Once all the processes have finished, the loop repeats infinitely. The transitions T2, T3, and T4 represent the activity load of each process. There are different approaches to add an amount of time to these transitions. Within a suitable simulation process, this allows to investigate the performance of the system under different workload conditions, which is a must in the development of real-world solutions. Once the parameters of the model have been tuned and its performance evaluated, the next step consists on the synthesis of the code in a target programming language for a specific platform. A Petri net model representing three parallel threads. The threads are launched in parallel by the firing off one. Each thread runs free to complete its activity. In this design, the end of the threads is synchronized at 5. That is, if one thread finishes its work before the others, it must wait until the other threads end its activities. Once all the threads have finished, they are reinitialized to repeat the loop. For example, shows a section of code in C++ implemented from the model in. The code implements a set of joinable POSIX threads. A for loop launches a number of threads defined by the global constant num_threads. Other for loop waits for the end of the threads. Once all the threads have finished, the loop repeats indefinitely. The automatic code generation from Petri net models has recently been investigated with promissory results. A section of code in C++ implemented from the Petri net in the figure above. An infinite loop initializes a set of joinable threads. A for loop launches the number of threads specified by the constant num_threads. A for loop waits for the end of all the launched threads. This cycle repeats forever.